So we'll get on with the second talk now. Excellent. And I'll just hand it over to James Reed, who's here from Oxford, and take it away, please.
Yeah, thanks Nick and Kaiser, and thanks for having me. I've had a great time. So today I'm going to be talking about background independence, and in particular whether bulk theories in gauge gravity dualities are background independent. I guess I was motivated to look at this as a result of reading some recent papers by Sebastian Dahar and his collaborators, where they claim that such theories are background independent. What I want to do is subject those claims to critical scrutiny and also see whether they continue to hold on other definitions of background independence, such as those of Belot and Pooley. So the way the talk's going to pan out is that in the first third, I just want to give some basic setup, talking about models of scientific theories. I want to introduce a notion of Diffeomorphism invariance, because this concept's intimately tied up with background independence. And then I want to talk about some naive definitions of background independence, which can be seen to fail for fairly obvious reasons. On the back of that work, in the second part of the talk, I'm going to talk about three more sophisticated definitions of background independence, those due to Pooley, Belot, and Dahar. And then in the third part of the talk, I'll apply that to the case of bulk theories in gauge gravity dualities in order to assess whether they are background independent or not. So let's start with the setup. So a pretty familiar notion in the literature is that of a kinematically possible model. So this is a tuple of geometrical objects. So for example, in general relativity, the kinematically possible models are picked out by these triples M, G, phi, where M is a four-dimensional differentiable manifold, G is a Lorentzian metric field on that manifold, and phi is a schematic placeholder for the matter fields of the theory. But within the kinematically possible models, we might want to talk about some dynamically possible models. And these are those kinematically possible models, the geometrical objects of which satisfy certain dynamical equations. So in GR, the dynamically possible models are those kinematically possible models, the geometrical objects of which satisfy the Einstein field equations. So these two notions are reasonably familiar from the literature. In this talk, I want to introduce a third class of model. These I'm going to call the boundary possible models. So these are the kinematically possible models which satisfy certain specified boundary conditions. So for example, we might specify that the metric field be asymptotically flat. So with these three types of models in hand, we have a picture that at the moment looks something like the following. We have the kinematically possible models, and then within that, the dynamically possible models and the boundary possible models. And at the moment, it's not completely clear how these dynamically possible models and boundary possible models overlap. But that's something that we'll talk about later on. We don't need to worry about it too much just yet. Okay, so with that idea of models of a scientific theory in hand, we can then talk about two kind of toy theories, which Pooley talks about in his recent paper on background independence, which can be very useful in assessing whether a definition of background independence is a good one or not. So the first of these we call SR1. Kinematically possible models of this theory are picked out by a triple M eta phi, where M is a four-dimensional differentiable manifold. The eta is a metric field which is fixed to be the Minkowski metric in all kinematically possible models, and the phi is a real scalar field. Then the dynamically possible models are picked out to be those which satisfy this massless Klein-Gordon equation for the phi. So the important thing to note about this theory, as I just said, is that the metric field is fixed to be the Minkowski metric in all kinematically possible models. So as Pooley says, so understood, this Klein-Gordon equation isn't an equation for eta and phi together, rather it's an equation for phi given eta. So it's useful to set this in contrast with the second toy theory, which is SR2. Here, kinematically possible models are triples M, G, phi, where G is now a generic, not necessarily Minkowski Lorentzian metric. But now we have two dynamical equations which pick out the dynamically possible models. We again have a Klein-Gordon equation, but we also have this second equation which fixes the metric field to be flat in the dynamically possible models. So in this case, flatness of the metric is fixed dynamically by the second equation, whereas in SR1 it was fixed at the level of kinematically possible models. So Pooley says of SR2, it's important that these two equations are understood as coupled equations for phi and G together. So for these theories, the dynamically possible models coincide because in both cases we have a flat metric and a scalar field which obeys the Klein-Gordon equation. But the class of kinematically possible models of SR2 is much bigger than that of SR1, because in SR2 we're allowed any old Lorentzian metric, whereas SR2 we're only allowed Minkowski metrics. So we kind of have a picture which looks like this. Okay. So now the final thing that I want to introduce before we can get onto the main bit of the talk is the notion of Diffeomorphism invariance. Of course, there's a big literature on this topic, so again, I'm just going to give you one definition, and again, this will be following Pooley's paper. So Pooley defines diffeomorphism invariance in the following way. A theory is diffeomorphism invariant if and only if this model M, F, blah, 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 D, blah, 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 where the F's are fixed fields in the sense of the metric of SR1 and the D's are dynamical fields. If that model is a dynamically possible model of the theory, then so is this second model where we've done an arbitrary diffeomorphism on the dynamical fields of the theory. So on this definition, it turns out that SR1 is not diffeomorphism invariant, because if M eta phi is a dPm of SR1, then in general M eta d star phi won't be a dynamically possible model. However, SR2 is diffeomorphism invariant. So now that we've got all this set up in hand, we can start to assess various definitions of background independence. So let's start off with some pretty naive definitions. First of all, maybe background independence is just the same as diffeomorphism invariance. But SR2 seems to be a counterexample to this, because SR2 is intuitively background dependent. The metric field is fixed to be flat and non-dynamical in all kinematically possible models. Nevertheless, the theory is diffeomorphism invariant. A second idea would be that maybe background independence is the same as having no fixed fields, but again, SR2 doesn't have any fixed fields in the sense of SR1, but it's intuitively not background independent. So it seems like we're going to need some more sophisticated definition of background independence. And this is where these definitions of Pooley, Haro, and Belot come in. So in this next part of the talk, I'll briefly review these before getting onto holography in the third section. So the way that Pooley talked about background independence is the following. He says, a theory is background independent if and only if its solution space is determined by a generally covariant action, all of whose dependent variables are subject to Hamilton's principle, and all of whose dependent variables represent physical fields. So in the case of SR1, these fixed fields, in this case the Minkowski metric, isn't subject to Hamilton's principle. So SR1 violates this condition 1 in the definition of background independence, as will any theory with fixed fields. But the case of SR2 is a little more subtle. It used to be thought that there was no action, no generally covariant action for this theory. So in that case, SR2 would straightforwardly violate the definition of background independence. But then Rosen came out with an action that does, which looks like this. By the way, I realized that I forgot the term for the phi field, so you can imagine adding in a L phi piece here. But Pooley argues that, in fact, even with this action, SR2 still violates the definition of background independence because this Lagrange multiplier field theta that we introduce isn't physical. So it seems like Pooley's definition does deliver the right verdicts on SR1 and SR2, although kind of by the skin of its teeth in SR2. Okay. So a quite different approach to background independence is that of Belot. Belot's approach is actually reasonably subtle and quite difficult to state precisely, so it's worth warning you that this is a pretty stripped down version, but hopefully it's enough to give you the gist. So we start off by considering kinematically possible models of some theory, and we'll denote these M, O1 to ON. We identify some geometrical structure in the models, and we'll label that by OG. So this would be reasonably easy to do in a lot of theories. So for example, in general relativity, it's reasonably easy to point to the metric field as representing geometrical structure. Then we say that the geometrical degrees of freedom of the theory are those degrees of freedom needed to parameterize the variation of the OG across models. So if we think about, for example, SR1, then because the metric field is the same in all dynamically possible models, there are actually no geometrical degrees of freedom in this case, because we need no degrees of freedom to parameterize the difference in the geometry across the models. Similarly, we say that the physical degrees of freedom those degrees of freedom needed to parameterize the variation of all of these O's across the models. So ultimately, the idea is that, Belot says that a theory is background independent if all of its physical degrees of freedom correspond to geometrical degrees of freedom. The idea is that each unique configuration of the physical fields has to correspond to a unique configuration of the geometry. This seems to be satisfied in general relativity, where a different configuration of the physical fields via the Einstein field equations leads to a different configuration of the geometry. But it's not satisfied by SR1 and SR2, because in that case, we have all these different inequivalent configurations of the physical fields, but we only have the same geometry in every case. So the number of physical degrees of freedom is bigger than the number of geometrical degrees of freedom, because in fact there are no geometrical degrees of freedom. So the theory turns out to be background dependent. Both of these theories turn out to be background dependent on Belot's definition. One thing that's interesting about Belot is that his approach is able to deliver kind of intermediate verdicts on background independence. So as I said, in general relativity, it seems like we do have this case where every physical degree of freedom corresponds to a geometrical degree of freedom. But then he says, so suppose that we impose some asymptotic or some kind of boundary conditions on the geometry of the theory, so for example, asymptotic flatness. Then we reduce the number of geometrical degrees of freedom in the theory by a finite amount. So it turns out that such otherwise background independent theories, but with boundary conditions, are nearly background independent. And Belot makes this precise in a technical sense, but hopefully this is enough to give the gist. So I think that Belot's approach to background independence is pretty nice, but it's worth flagging at least one problem. So it seems like you can construct a theory where in every kinematically possible model, we have a fixed geometry that is different in every kinematically possible model. Then it seems like each unique configuration of the physical stuff corresponds to a unique configuration of the geometry, but nevertheless, it seems like the geometry is fixed background in every model. So I think this kind of theory is maybe a problem for Belot. Maybe that's something that we can discuss. But anyway, hopefully this is enough on Belot for us to get by when we end up talking about dualities and holography. So the third definition of background independence, and probably the one that we're going to focus on the most, is that of Dahar. So he says a theory is background independent if it satisfies the following requirements. First of all, the dynamical laws of the theory have to be generally covariant, by which he means Diffeomorphism invariant. And secondly, the dynamical laws don't refer to any background fields. The novel condition is this condition 2. Basically, what this is saying is that the quantities of the theory, maybe tensors, have to transform appropriately, i.e. tensorially, under diffeomorphisms, and also don't refer to any background metric. This would seem to be almost trivially satisfied in the case of a classical theory. But it turns out that in a quantum theory, due to the presence of anomalies, we can get interesting results here. So let's just quickly talk about how Haro does with SR1 and SR2. Well, SR1 straightforwardly violates 1b, which is a prohibition on fixed fields. But there, I think, is a problem with SR2. It seems to satisfy this definition, but we don't want it to satisfy a definition of background independence. So this seems to be an obvious problem for this kind of definition. But to be conciliatory, I will set it aside in the remainder of this talk. So one last thing on Haro, which is a kind of question for the audience, is that personally, I don't see why this condition on the quantities transforming appropriately is relevant to the idea of background. So I don't see why this condition 2 is included in a definition of background independence. Perhaps someone has some insight here or I'm missing something, in which case I would like to hear it. Okay. So now that we've got those definitions of background independence, we can turn our attention to holography. So let's just remind ourselves of a holographic duality. This is a duality, i.e. some kind of theoretical equivalence between a theory defined on a d-dimensional spacetime, the bulk, and a theory defined on a d-1 dimensional spacetime, which forms the boundary of that bulk. In the specific case where the theory defined in the d-dimensional spacetime is a gravity theory, and the theory defined in the d-1 dimensional boundary spacetime is a gauge theory. We have a so-called gauge-gravity duality. In turn, the most famous example of gauge-gravity duality is the ADS-CFT correspondence, where the theory in the bulk is a string theory in anti-de Sitter spacetime, and the theory on the boundary is a conformal field theory. One thing to note is it's actually sufficient for the bulk theory to be asymptotically ADS. So this is what we're going to mean when we talk about the boundary condition on the bulk. And in what follows, we're going to mostly have this example in mind. So one thing that's interesting about these ADS-CFT cases is that the bulk theory can be subject to a so-called Diffeomorphism anomaly. And this is something which Haro points out. So to understand what's meant here, let's first distinguish between two types of diffeomorphism. First of all, diffeomorphisms which preserve the asymptotic form of the metric, and second, diffeomorphisms which act on the asymptotic metric by a conformal transformation. Now, if in specifying the bulk theory, we specify the boundary conditions, i.e. we specify its class of boundary possible models, then it's clear that diffeomorphisms of type B are going to take us out of that class of boundary possible models because they do something to the boundary. But what's really interesting about these diffeomorphisms of type B is that when the dimension of the boundary is even, physical quantities of the bulk theory, like the stress energy tensor, don't transform appropriately or as expected under diffeomorphisms. In fact, they pick up extra terms, and this is a manifestation of the diffeomorphism anomaly. And we can see that maybe this would have some tension with criterion B in Haro's definition of background independence. So let's now look at how such bulk theories do on Haro's definition. The first thing to say is that they don't obviously contain any fixed fields, so it seems like that criterion that there be no fixed fields is satisfied. The second thing to say is that the theories are diffeomorphism invariant, potentially up to these diffeomorphisms which somehow change the asymptotic form of the metric. This might seem to be in conflict with the criterion that the theory be diffeomorphism invariant, but Haro doesn't think it is. He says that by specifying these boundary conditions for the theory, we determine the parameter space of the theory. Any diffeomorphisms which change the boundary conditions are simply irrelevant to our appraisals of whether the theory is diffeomorphism invariant or not. This is something that I have some worries about, which I'll shortly talk about. But the idea is that if we can spin some kind of line like that, then we can still claim that the theory is diffeomorphism invariant. And indeed, it's clear that once you make that kind of move, you can also make that move to avoid the problems with the diffeomorphism anomaly, because the diffeomorphisms which led to that problem in conflict with Haro's criterion 2 are precisely diffeomorphisms which also change the boundary in some way, so we can ignore those as well. That's Haro's line of how he ends up saying the bulk theories are diffeomorphism invariant and thereby are background independent. So I have some kind of ill-formed worries about Haro's claim that we can ignore these diffeomorphisms which take us out of the class of models with specified boundary conditions. First, just to introduce some terminology, it seems like if we have general relativity with some boundary conditions, asymptotic boundary conditions on the metric, then it's reasonable to call that a theory. But in some sense, GR is the more general supertheory of that theory. This is just terminology. So I guess my worry is not maximally clearly put in the slides. I don't know if people in Geneva will be able to see if I write on the board. The idea is, I'll try. So Dahar says, suppose we have some model which satisfies both the dynamical laws and the specified boundary conditions of the theory. Then if we do a diffeomorphism on that model, do we stay in the class of models which satisfy the dynamical equations and the boundary conditions? He says that, but he also says that any diffeomorphism which takes us out of the class of models which satisfy the boundary conditions is irrelevant. but suppose that we do have something like this, then it seems like even though the theory with boundary conditions is background independent on Dahar's definition, the fact that the supertheory has some case where you can do a diffeomorphism that takes you from a dynamically possible model to a not dynamically possible model means that the supertheory isn't background independent on Dahar's definition. So it seems like Dahar is giving this weird result where the supertheory can be background independent, but the subtheory can be background dependent. And it just seems weird to me that you can impose more structure and yet increase the background independence of a theory. So yeah, I probably went through that a bit quickly, but maybe this is something that we can talk about. And maybe it's ultimately fine, but it's just some kind of niggling worry that I have about this line that Dahar is telling us. So thankfully, just to wrap up, it's a bit faster to talk about how bulk theories and gauge gravity dualities fare in on the definitions of background independence due to Pooley and Belot. So for Pooley, we had to ask these questions. Is there a generally covariant action for the theory? Are all dynamical variables subject to Hamilton's principle? And do all dependent variables represent physical fields? Maybe there's nothing a priori stopping the bulk theories from satisfying this definition of background independence. But maybe there's also a worry that any theory with boundary conditions is probably going to be pretty hard to get from such a action principle. So maybe any theory with these boundary conditions isn't going to come out as background independent on Pooley's definition. This is something that, again, might not pan out on it, but I think is worth thinking about more. Finally, on Belot's definition, it's actually pretty straightforward. The bulk theories come out as nearly background independent on the sense that we talked about earlier. So just to wrap up, Haro tells us that bulk theories and gauge gravity dualities are background independent, but we've seen that there both exist worries regarding his definition of background independence. It doesn't seem to deliver the right verdict on SR2. And there are worries regarding this kind of story that he's telling us about why we can ignore certain types of diffeomorphism in the bulk theory. On Pooley's account, maybe there are problems for the background independence of the bulk theories due to their specification of certain boundary conditions. And on Belot's account, bulk theories are nearly background independent. Okay, that's it. Thank you.
Okay, so stay up there so they can see. Do you want to take give some questions from over there first?
I have a question. So if you go back to Belot's account and the problem you tried to raise for this, with cherry-banded theories, I didn't quite understand what the problem was. So we're dealing with theory such that for each model in that theory, or kinematically possible model, the metric is fixed, but it's distinct, in general distinct from model to model.
Yes, that's right.
Isn't GR like that as well? I mean, in a model, there is one. Yeah,
that's precisely right. The issue is that so GR comes out as background independent on Pooley's definition, on Belot's definition. The problem is that this theory here, this intuitively background dependent theory, because the metric is fixed, is also coming out as background independent on Belot's definition, and that doesn't seem right.
But what do you mean by the metric is fixed?
So,
in a general relativistic model, say in the center spacetime or in a cosmological model or any one of these models, the metric is fixed as well. It's given. It's there. So you mean something different?
I mean, I guess I had the idea that in these models in this apparently problematic theory, the metric is fixed at the level of kinematically possible models. It doesn't, and thereby does not react to the presence of matter in any way. Whereas in general relativity, that's not the case. There's some dynamical equation which relates the metric to the matter fields. So that's a kind of distinction between two theories.
I see. Ollie has a finger.
Yeah, so how many models does this theory have? Does it have one, or maybe one up to isomorphism?
I guess you could, you could probably get by with it only having one.
So if it has more than one, then it seems it's not going to be background independent.
Why not? Why not?
Because if it's got more than one, then there are going to be some physical degrees of freedom. But if there's only one geometry, then there aren't any geometric degrees of freedom.
But you can imagine that, so suppose that it has two models, and in one it has the Minkowski metric, and in the other model it has some inequivalent metric. Then there's not only one geometry in that case.
Right, so but then it has geometrical degrees of freedom.
Yeah.
Their dynamics may be insensitive to the matter of the model, but there are still geometrical degrees of freedom required to...
Yeah, I think I agree with you. So it comes out, but do you not share the intuition that such a theory is background dependent?
Right, so the geometry being dynamical. So I do have that intuition. I think there's a distinction that Belot's missing between the geometry being dynamical and the geometry's dynamics being sensitive to other stuff. And there's something else that's
Okay.
missed in Belot's.
Yeah, maybe it's better to try and construct something which more obviously illustrates this. But
Julius?
Just a quick question about the example of the theory, of the kind you have in mind, or at least, or maybe, or perhaps a question whether I understood it correctly. So an example of a theory which would be problematic for Belot's account, that be just those and exactly those spacetimes GR which are Ricci flat. So then we still have a lot of solutions. I think uncountably many, but there is some sort of background in the sense that we require that the stress and tension momentum tensor is zero, and that's background according to our intuitions. Could that be an example of what you had in mind?
Potentially yes, but I guess it hinges on whether by restricting to Ricci flatness you can have multiple models with equivalent geometries but inequivalent configurations of the physical stuff. But I don't see how. Yeah, I think you might be right. If you're just restricting to a subclass of models of GR by some extra condition.
So I'm just taking a smaller set of relativistic spacetimes, so not the full set of GR, but the smaller one.
Yeah.
That it's a subset, it's a smaller one, but cardinality-wise, it's still as large as possible. So yeah, perhaps that could be used to generate some problems.
Yeah, it seems like that extra condition is some kind of background which Belot's definition isn't sensitive to. Yeah, if you're just using the extra condition to restrict the class of models from GR, then potentially I'm in agreement.
Because that's kind of like restricting our attention only to the class of solutions, for example. We restrict our attention to the Ricci solutions. It's restricting our attention to that solution. That makes sense.
Say that again, that you're breaking up.
So in that sense, I think that the restricting attention to the vacuum, to the Ricci flat solutions would be somewhat analogous to restricting our attention to the dust solutions or perfect fluid solutions only, because then the dust or the fluid would be the thing that is, in some intuitive sense, not changing between the solutions. The very fact that it's dust or fluid or whatever.
Yeah. Yeah, I think you might be right.
Can I ask a question?
No, not from here. Sorry, Pooley.
I'm going to ask a question. Well, we're going to have a couple of questions here, I think. Ollie gets to ask him questions all the time, I think, right? So, can you just talk through what's going on in the ADS CFT case? Because the definitions you've given are all classical, but ADS CFT is quantum.
Yeah. So
how is the quantum? I mean, how are the definitions made to apply to the quantum case?
Well, the first thing to say is Dahar's definition is maybe a little bit quantum because of this second point.
Okay.
But yeah, I mean, okay. So let's just go to Belot's. I mean, there doesn't seem to be anything which necessarily requires you to be talking about a classical theory here.
So what was number one? So just the slide before that, then, I guess. But this looks classical, right? Or
I mean, it depends how you pick out dynamically possible models. Probably not by just a straightforward field equation, but by I don't know, a path integral or something. But
okay, so but here, so I might think of the O's here as sort of operators or something, and then what we're talking about is variate their expectation values or something, and parameterizing.
Yeah, I mean, I think this is definitely worth thinking about more, and it's on my to think about list. But yeah, maybe you can still think about them as fields, but then your dynamically possible models are those for which the correlation functions of those fields look like some specified thing.
Okay, so that's how I should be thinking of the later arguments or something like that.
I guess so, yeah. But
okay.
Yeah, it's possible that there might be some subtleties in fleshing this out for a quantum theory.
Okay. Keizo has a question.
Yeah, I was thinking about what the Haro what these people do. I'm kind of worried that in some sense they might be asking the wrong question. Because what he's talking about the background dependence of the bulk theory. But if the duality is exact, and if one also has that view that they actually describe the same reality, and you're talking about the background dependence of that kind of target prima facie space picture in one of those.
Yeah.
And why is that kind of even relevant? And shouldn't it be the case that if the bulk is background independent, the boundary theory would then also have to be background independent in a relevant sense? And perhaps one shouldn't really try to apply these kind of background questions, especially, I mean, for instance, Nick's written this paper where target space shouldn't be identified with space, and I also have that view in a much more general setting that should be applied across the board on string theory. And then it might be that the question about background dependence must be addressed at the level of that kind of shared structure or the shared physical content, and not in terms of those two classical pictures.
I think you might be right that ultimately it's going to be more useful to be thinking about the shared structure, but it doesn't stop us looking at these two dual theories and treating them as a flat-footed realist about them and see what their own commitments are.
Sure.
Also, your point about the conformal field theory also being background independent as a result of the bulk theory being background independent. If you take that line of being a straightforward realist about the two theories, then I think you should be a bit wary about mapping properties of one theory. But ultimately, how meaningful or useful it is to be talking about these rather than the shared structure. There I have sympathies with you, I think.
Yeah. What I meant was when I said the other theory also have to background independent, my point there was only in the relevant sense that I'm looking for in the deep shared structure. And because we know in dualities, like things that aren't physically relevant, like gauge symmetries don't always have to be preserving one in those mappings, so that's kind of okay. But what I meant was that since it is different in this case from one to the other,
yeah,
and we also think that only that physical shared one is the physical interesting one,
yeah,
then we know that that question about the background independence in these two
sure.
is asking the wrong question.
Sure, yeah.
At the more
that's it.
fundamental
Yeah.
level.
Yeah.
That is kind of the point.
Yeah, and just to add to that, like nothing in this presentation really gives any verdict on what the background independence of a theory only consisting in the shared structure is going to be.
Okay,
like.
good. Thank you.
Yeah.
Over to you. Back to Ollie, I guess, if you've got somebody else in Geneva.
Am I now? Well, actually, I just wanted you to say again the key part of your talk, which I missed, which is this dodgy move that Dahar makes. Just restate that.
Well, I'm not sure if it's dodgy or not, but okay, yeah. So it would be much easier if I could draw a diagram. Is there any way of?
You have that diagram. You could.
Okay. Well, actually, you can just add.
I can show it. It's, I'll move the cursor.
Yeah,
Can you
okay.
see the cursor over there?
So imagine that you have some diffeomorphism which takes us from this intersection of D and B to just a point in K. Then Haro says we can ignore those diffeomorphisms because they take us out of B. But in that case, if we spin that kind of line, then we might end up saying that the theory with the boundary conditions is background independent, because for all the diffeomorphisms which aren't excluded in this way, the theory is diffeomorphism invariant. But nevertheless, the theory without the boundary conditions, what I call the super theory, is not background independent, because you have some diffeomorphism which takes us out of D. Which just seems weird that by imposing boundary conditions you increase the background independence of a theory.
So, would this be a fair analog if you consider SR1?
Yeah.
And you consider a different definition of diffeomorphism invariance, which so you could consider diffeomorphisms that act on the fixed fields as well as the non-fixed fields.
Yeah.
And you note that they throw you out of K. So you could say, well, let's just ignore those because they throw you out of K, and then you would get the result that SR1 was invariant because you're only allowed to consider diffeomorphisms which are.
Yeah, I think that is a fair analog.
So that seems analogous, but with
Yeah.
K playing the role of B.
Yeah, I think that's right. And that also seems a bit dodgy because it delivers.
Yeah.
Yeah, I mean, if you're saying it's diffeomorphism invariant up to all the diffeomorphisms which pose a problem, then it seems a bit cheap.
Yeah. I have one more question. If that's, is there anyone else in Geneva? I don't see any more hands there.
No, not from me.
So, I mean, I guess so. The game is so there's several different definitions of what background independence might be, and then sort of intuitions about how they should settle different cases.
Well, not quite.
But ultimately, what should be driving those intuitions? I mean, we sort of talked a little bit about this before.
Yeah.
People sometimes think about this, right, in terms of, well, GR taught us something really important about background independence.
Yeah.
As a sort of criterion for quantum gravity, or.
Yeah.
And the game here is sort of trying to figure out what it was that it taught us.
Yeah, sure. So I guess on the one hand, you can divorce yourself from any intuitions and just treat these definitions of background independence as like abstract criteria and see whether bulk theories satisfy them. But then, as a separate project, you might, if you have any faith in your intuitions, you might want to use them to guide you to choose a definition of background independence. But you know, I think I'm sympathetic to your skepticism.
I mean, put the way I do, it's going to be kind of hard, isn't it? Because we have general relativity, so we have exactly one case of background independence.
Yeah.
Presumably, all these definitions get that one right.
Yeah, almost by stipulating. Yeah.
It's not like say in quantum field theory and renormalization. I mean, there's a whole bunch of cases that are renormalizable or not, and you kind of know what it.
Yeah, I think.
So how are you supposed to generalize from the sort of one case to the thing that's?
Yeah.
Maybe you don't have an answer. Did you see that as a question? I guess.
I mean, yeah. You might think that general relativity is the most obvious case, but then these theories like SR1 and SR2 seem to be. We seem to have reasonably strong intuitions about their background independence or not. So, to some extent, we can use those as extra cases to kind of guide our construction of a definition.
Yeah, but we have to sort of but that's because I guess we look at the case of GR and then in our own minds kind of construct some sort of generalization of what that background independence is.
Yeah.
But why would we have any faith that we were actually latching on to sort of the physical principle that was background independence rather than something that was whatever more amenable to human reasoning or something?
Yeah, I feel some skepticism towards these when people claim that a theory must be background independent. I don't really get that. So yeah, I don't think there's anything floating out in the world of background independence. Rather, it can be a kind of a useful way of talking about theories and evaluating them and learning things about them.
Yeah, okay, I mean, I totally agree with that. I'm not trying to be sort of skeptical about the project in general at all, just trying to get some context for how we should think about what's going on.
Okay.
That's cool. I think we're done with questions here, and we're kind of coming towards the end of time. Is any last questions in Geneva?
Well, I have one if I'm allowed. When you say Dahar classify SR2 as background independent?
Background,
right?
Yeah, I think that's right, yeah. Oh, I'm moving the thing now.
Dang it. Sorry, I think that back. Try that now.
I was wondering whether that was because you had stipulated that by background field he meant fixed field, and I wondered whether that is what he meant, because it could mean Andersonian absolute.
To go back to pointer.
It's possible that you're right. I remember reading Dahar and thinking that what he said mapped more closely onto the idea of a fixed field than an absolute object. But it's certainly worth double checking, and I guess it's certainly worth seeing, maybe coming up with an alternative definition where we replace that criterion with absolute objects and see what happens. But yeah, if I trust my past self, then I don't think he meant absolute objects.
We have one last question here, Julius.
Since I wanted to snatch this one from Holly. I mean, it's a comment on what Nick said, that GR is the only example of background independence that we have. But I think we could easily come up with more examples, and if you just look at, for instance, FR gravity theories or teleparallel gravity, that also probably would be background independent, right?
Yeah, I think you're right that.
That's much wider class of examples that needs to be considered.
Yeah, I looked at teleparallel gravity a bit, and I also ended up thinking that it was also background independent. So yeah, I don't buy the line that GR is the only background independent theory that we know of.
I mean, it's the only sort of empirically successful one that we know of.
Well, maybe, but there are some versions of telebarrel gravity that are equivalent to GR anyway, so.
If
Okay.
some conditions apply to those units, who knows what happens to be the case there.
Yeah, I didn't quite hear that. But
Yeah. Okay. Okay.
okay.
Shall we call it a day?